Gnanam paramam dheyam. Knowledge is supreme.
All right. In the last lecture, we saw that a particular polynomial of degree 2, x square plus 1, as a polynomial with real coefficients, this polynomial is a prime polynomial, and which is equivalent to the fact that this polynomial doesn't have a zero inside the field of real numbers. I want to generalize this, or I want to analyze for a general field, when can this particular polynomial is prime polynomial in kx, or equivalently when can this polynomial has no zero inside the given field k. So, we are going in this example, we are going to analyze this situation. Example, k field, and we consider this very special polynomial x square plus 1. This is a polynomial of degree 2 in the field k over a field kx over a field k. So, it is a polynomial in kx. So, when exactly x square plus 1 is a prime polynomial in kx. This is equivalent to saying the zeros of this polynomial inside k, there is nobody, this empty set. So, this means, so that is x square plus 1 has no zero in k. This is what we want to analyze. For example, when we take a field k to be equal to the finite field z mod p, where p is prime, in this case we want to analyze. So, that will give us extensions of the field z mod p of degree 2, because this is a degree 2 polynomial. We prove the following lemma. So, this is a lemma. Let p be any prime number, p belong to p, be a prime number, and consider the polynomial x square plus 1 as a polynomial in z mod p x. Then x square plus 1 has no zero in z mod p. We have seen that this is equivalent to saying x square plus 1 is a prime polynomial in z mod px. This was we have seen, we have just remarked above, but this is equivalent to saying in terms of the numerals, this is equivalent to saying p is congruent to 3 mod 4. So, that is 4 divides p minus 3. That is equivalent to saying this. All right. So, let us test for few small values of p. Let us take p equal to 2. Then p is not congruent to 3 mod 4, P is congruent to 2 mod 4. But then in this case x square plus 1 is same as x plus 1 whole square, because P is a characteristic. So it is this, and therefore this polynomial actually has a 0. 1 is a 0 of x. So in Z mod 2x. In Z mod 2x actually this x square plus 1 splits into linear factors. Alright. If such a thing one has to test for p equal to 3, then p is indeed congruent to 3 mod 4. Therefore, by our observation, this lemma, this x square plus 1 is a prime polynomial in Z mod 3x. This you can test very easily, because this is a degree 2 polynomial. If it is not prime, then it will have a 0, and the only possibility for 0 is 0, 1 and 2, because these are the only elements of Z mod 3. And to check, take each one of them and plug it in here and see whether it is 0 or not. So when you plug it x equal to 0, this is 1, which is not obviously not 0. If you plug it in 1, then it is 1 plus 1 2, which is definitely not 0. And if you plug it in 2, that is 2 square is 4, 4 plus 1 5, 5 mod 3 is 2, which is not 0 again. So therefore this is a prime polynomial in Z mod 3x. Alright, so we prove this. So proof of lemma. Lemma has two parts. So we will first prove this way. That means we will suppose P is congruent to 3 mod 4, and we want to check that the polynomial x square plus 1 has no 0. To prove that, x square plus 1 has no 0 in Z mod P. No. Alright. So suppose it is a 0. So suppose if x in Z mod P is a 0 of x square plus 1. So that means when I plug it in capital X equal to small x, it becomes 0. X square plus 1 is 0. But definitely this x is not 0. Because if x were 0, then x square plus 1, this is 1, and 1 equal to 0 is not possible. So x is definitely not 0. And this equation will tell you x square equal to minus 1. But then x is a non-zero element in the field. So x belongs to ZP cross. This is a group, because Z mod P is a field, and this is a group of order 1 less element than Z mod P, that is P minus 1. So this is a group under multiplication of order P minus 1, and x is one element there, such that x square equal to minus 1. So therefore x4 will be equal to x square, but x square is minus 1 and minus 1 square is 1. So x power 4 is 1. So this means the order of the element, small x in the group Z mod P cross is 4, because x is not 1 and x square is minus 1. So therefore the smallest power of x, which becomes identity in the group, is precisely 4. So order x is 4. But let me recall, I want to use here a very easy theorem. In fact, it is the first theorem when one starts studying finite groups. The first ever theorem is called is due to Lagrange. So this is Lagrange theorem that says that let G be a finite group, G be a finite group of order n, that is n is the cardinality of G, and G is an element in G, then the order of G, small g, divides order of G, which is n. This is known as Lagrange theorem. Lagrange have discovered this theorem while he was studying the relations between the roots of a polynomial and the coefficients of the polynomial, and especially when he was dealing with rational function fields in many variables and the permutation group operating on this and studying the fixed points, etc., etc. During that time he has guessed the theorem, which is of course very easy to prove but Lagrange never dealt with groups. Okay. So we have the situation x was an order, an element in Z mod p cross, and order of x is 4. But then 4 should divide the order of Z mod p cross. But Z mod p cross is order p minus 1. So 4 should divide p minus 1, but this is equivalent to saying p is congruent to 1 mod 4. But our assumption was p was congruent to 3 mod 4, which contradicts our assumption that the polynomial x square plus 1 has a 0 inside this. So therefore we have proved one-way implication. Now conversely, we proved if p is congruent to 3 mod 4, then Z mod px modulo ideal generated by x square plus 1, this is a field. It is an extension field of Z mod p, and the degree of the field extension is 2. So in fact degree of Z mod px modulo the ideal generated by x square plus 1, this field over Z mod p, this degree is 2. This is exactly like real numbers, complex numbers case. Now we want to prove the converse. So we want to prove this way. So that means we want to prove that, so suppose x square plus 1 in Z mod px is a prime polynomial, and we want to prove, so to prove from here that p must be congruent to 3 mod 4. This is what we want to prove. So suppose not. Suppose p is not congruent to 3 mod 4. So what are the possibilities for p? Then p cannot be congruent to 2 mod 4 because p is a prime number. So therefore only possibility is p has to be congruent to 1 mod 4. Since p is prime, So, once P is congruent to 1 mod 4, that means what? That means 4 divides P minus 1, and we are in this group now, Z P cross. This is a group of order P minus 1, and I want to use the fact that this group is cyclic. We are going to prove this. We will prove later in our lectures that this group Z mod P cross, this group is cyclic. And I have a we have a divisor 4 of this order of this group. So, and since 4 divides P minus 1, there exists an element X in this group such that order of that element, order of X equal to 4. This is true because in every cyclic group, every divisor of the group, order of the group in a cyclic group, in a finite cyclic group, for every divisor of an order of the group, there is an element of that order. So that's what I have used. This is a cyclic group, 4 is a divisor of the order, therefore there is an element X in that group of order 4. Once we have this, order is 4, so x raised to 4 is 1, but then order of, what will be the order of x square? Order of x square has to be 2. Minus 1 is an element in Z mod P cross. And what is the order of minus 1? Order of minus 1 is also 2. But then there is only, in a cyclic group of even order, there is but in a cyclic group of even order, there is exactly one element of order 2. But here we are likely that 2 elements, x square is 1 and minus 1 is other one, which are likely of order 2. So therefore x square has to be minus 1. But that means this x square plus 1 is 0. So that means x is a 0 of the polynomial x square plus 1. So that is what we wanted to prove. That is what we wanted to prove. So we finish this proof of this lemma, but this proof also one can directly also see as follows. Direct proof. Look at x equal to, look at p minus 1 by 2, this factorial. Look at this element. Then we know x square is p minus 1 factorial which is congruent to minus 1 mod p. This is precisely Wilson's theorem. So, remember what we wanted to prove. By assuming x square plus 1 is a prime polynomial, we wanted to prove p is congruent to 3 mod 4. By assuming p congruent to 1 mod 4, we got a contradiction because this is a 0 of this polynomial. That means this polynomial is not a prime polynomial, that is x square plus 1 is not a prime polynomial. In Z mod Px. This is a contradiction to our assumption. Therefore, P cannot be congruent to 1 mod 4. Therefore, P has to be congruent to 3 mod 4. So, altogether we have proved the lemma. Now, the next question is, if I have a polynomial mu with coefficients in the field, K field, and degree of mu is 2 or 3, how do you decide this polynomial mu has no 0 inside K? So, that is there is no 0 of mu inside K, but if there is no 0, that will mean that this polynomial has to be mu is a prime polynomial, because if mu is not prime, it factors. One of the factor has to be, because the degree is 2, one of the 2 or 3, the degree of mu is 2 or 3, therefore, one of the factor has to be linear if it factors. So, but it cannot be, because linear factors will correspond to the zeros of mu inside K. So, therefore, if there is no 0, the mu is a prime polynomial. That means, if I go modulo the polynomial ideal generated by the polynomial mu, this must be a field. So, you get a field extension, and this field extension, the degree of the field extension is equal to degree of mu. So, again you can simply test, let us take k equal to z mod 2, and let us take the polynomial mu to be equal to x square plus x plus 1. This is degree 2 polynomial, and now we want to test whether L is a field or not. This modulo mu. So, to test that, you just have to test whether 0 and 1, they are zeros of this polynomial mu, but to check that, I just put capital X equal to 0 and test. If I put capital X equal to 0, you get 1, which is not 0. If I capital X equal to 1, if I put 1 square plus 1, this is 1 plus 1, which is 2, which is 0, and the remaining 1. So, this is not 0. Therefore, this has no 0. Therefore, this L is a field. That is how one checks for the small values. Similarly, you can check for the polynomial x cube plus x plus 1, and in this case, in the earlier case, the degree of the field extension is 2 and it is over Z mod 2. Therefore, the cardinality of L will be equal to 4. In this case, once we check it is prime polynomial, then the degree of L over K will be 3, and therefore, L will have cardinality 2 power 3, which is 8. That is how one construct finite fields with bigger cardinalities. So, with this we will stop here and continue this lecture, and remember, two important things I have used in the above proof. One is easy one, which is Lagrange theorem for groups, which relates the order of the elements and order of the group. And the other one is little bit more serious, that the cyclic groups, if I take Z mod P field and look at the multiplicative group of Z mod P, that is a cyclic group. This is what we will have to prove in the coming lectures. Thank you very much.